everyone. So in the last video, we reviewed a different coordinate system called polar coordinates, where we saw that you can describe a point instead of using x and y, you can describe it using r and theta. And we also saw how you can graph different curves using a polar system rather than the Cartesian system that we're used to. So in this video, we're going to focus on now doing calculus with these types of graphs that we saw in the last video. So we're going to be learning both how to find the slope of a tangent line. So that's more, like a derivative type calculus. And then we'll also be learning how to find an area that is within a polar curve. And so that would be using integration. So I want to start by talking about how to find the slope of a tangent line. So I'm going to give you the formula first, and then we will see where it comes from after that. So basically what this formula says is that if, let me say it this way, the slope of the line tangent to a polar curve. So remember, polar curves, the way that we define them for the most part was in this form. We would have r expressed as a function of theta. And we'll see an example of this in just a moment. But if you have a graph defined by r is equal to a function of theta, and if you're trying to find the slope of the tangent line at a particular value of theta, so at a particular angle, the formula is going to be dy dx is equal to dr d theta times sine of theta plus r times cosine of theta. Oops. And that is all divided by dr d theta times cosine of theta minus r times sine of theta. And I know this probably looks really complicated. We'll see exactly where it comes from. Basically, it comes from the chain rule and the product rule, and we'll see an example in just a few minutes. So one thing I just want to point out before we get into kind of proving where this comes from is that similarly to with parametric equations, it might seem a little odd that on the left-hand side we have x and y when we're dealing with polar coordinates. And the reason for that is that dy dx is just kind of our universal way of saying the slope of a tangent line. Because when we're talking about slope, the definition of slope is basically vertical change over horizontal change. So when we find the slope, we're truly finding the slope the same, like a slope of 1 will look the same in polar coordinates as it will in Cartesian coordinates. The only difference is that how do we go about actually calculating that slope? Well, if you look at the right-hand side of this formula, it's full of thetas, right? And so we're not going to be plugging in any x or y values. We're just going to be plugging in theta. And so it's really similar to with parametric equations. We had with parametric equations, we had dy dx is equal to on, the left-hand side, but then the formula looked like this, right? This was how we found the slope of the tangent line for parametric equations. And so even though the left-hand side says dy dx, the right-hand side was actually a function of t. And so it's a really similar idea here. And actually, it's not only a similar idea, it really is kind of the same thing. So we'll see as we kind of prove this, that it actually comes directly from the parametric one that I just wrote down. Let me just scooch this down. That's for an example that we'll do in a few minutes. Okay, so let's actually prove this. So where does this formula come from? Well, basically, if anytime we're dealing with polar coordinates, we saw that there is a translation that allows us to go back to Cartesian coordinates, right? So we know that we can write x as r times cosine of theta, and we can write y as r times sine of theta. That's something we saw in the last video. And so what we're going to do is we're going to treat our function as basically a parametric equation. So we're going to think about our polar equation as being a parametric equation where x and y are functions of theta, basically. So we're going to treat our polar equation as a parametric equation and then instead of with the parameter being t, the parameter in this case is theta. I know that's probably a little bit confusing, but basically, why does that work? Well, remember that r is also a function of theta, right? R is some function of theta, and same thing here. And so really, we can express x and y entirely as a function of theta. And so, it's really not too different from what we were doing with parametric equations, where we were expressing x and y as functions of t. Okay, so if we can express our equation as in terms of parametric equations, well, that means that we can use that same formula that we had in the video about parametric derivatives, right? So we can say dy dx is equal to dy d theta over dx d theta, right? That's like exactly what we had as our formula for parametric equations. It's just that now I'm using theta as the parameter instead of t. Okay, so let's go and try to figure out what dy d theta and dx d theta are. So our formula for y, or our equation for y, is that y is equal to r times sine of theta. Okay, so how would we find the derivative of this with respect to theta? Well, we'd have to use the product rule, right? Because y is the product of r, which remember, r is some mystery function of theta. It depends on what your curve is, but r is defined as a function of theta. And so we have the product of two functions that are both functions of theta. And so we have to use the product rule. So how do we write down the derivative of the first part? Well, the derivative of r with respect to theta, we don't know what r is. R is some function of theta. For example, the example we'll do in a moment, just to kind of write this down so you have something to think about. This is r is equal to 1 plus sine of theta, right? So for example, in this case, we would be taking the derivative of 1 plus sine of theta. So that's what I mean when I say r is a function of theta. So in the product rule, we first take the derivative of r, and that's dr d theta, and we multiply that with sine of theta, right? That's just how the product rule works. And then what's the second part of the product rule? Well, the second part of the product rule, you take the derivative of the second part, so that's cosine of theta, and you multiply it with the first thing without taking the derivative. So we get dr d theta times sine of theta plus r times cosine of theta. And then similarly, if we know that we can write x as r times cosine of theta, then that means that the derivative of x with respect to theta is going to be equal to dr d theta, so first part of the product rule, times cosine of theta. And then now we take the derivative of cosine of theta, and that's going to be negative sine of theta, and we multiply that with r. So let me just kind of make a note here that these are both using the product rule. Okay, so now let's put those back in, and we'll see that we get exactly the formula that we expected. And let me just scooch this down one more time. Okay, so if we put these into our equation here, we get in the numerator dr d theta times sine of theta plus r times cosine of theta. And in the denominator, we get dr d theta times cosine of theta minus r times sine of theta. And that exactly matches what I wrote up here as our formula, right? So, where this formula looks very complicated, but it really just comes from this idea of rewriting this as a parametric derivative and then just using the product rule. So that's the product rule is really the reason that we have these kind of funny addition and subtraction going on. Okay, so let's look at an example here. And this just magically changed color. Okay, so let's say that we have the graph of r is equal to 1 plus sine of theta. So this I put this on your previous worksheet as one to graph. This is called a cardioid. So this is a pretty, like, I don't know, it's weird to say famous, but it's kind of a famous polar curve. So it's one of the types of different, we saw that sometimes you can get a circle, sometimes you can get like a floral kind of looking pattern. This is kind of another shape that you can get called a cardioid. The first thing I want to do is I want to find dy dx. So find the slope of the tangent line when theta is equal to pi over 3. So what's that going to look like on the graph? We'll calculate it ourselves in a second, but where are we going to find that on the graph? Well, literally you just go to an angle of pi over 3 and look at, what's the point on the graph at that part, right? So if we go to pi over 3, that's here. And so we see that the slope of the tangent line will look something like this. Oops, let me do that a little better. So we can expect that it's going to be a negative slope, right? Just based on kind of what the picture looks like. Okay, so how do we do this? Well, we just apply that formula. So the formula we found is that dy dx is going to be equal to dr d theta times sine of theta plus r times cosine of theta divided by dr d theta times cosine of theta minus r times sine of theta. Okay, so really the main thing we need to do here is we need to figure out what dr d theta is, and then we can just kind of proceed from there. So what is dr d theta? Well, we just go up and look at our equation and take the derivative, right? R is a function of theta, so taking the derivative of r with respect to theta is just like taking a normal derivative. So dr d theta is going to be equal to, so if r is equal to 1 plus sine of theta, what's the derivative of that with respect to theta? It's cosine of theta. And then the other thing we're going to need to plug in is r, right? And so what is r? Well, r is just 1 plus sine of theta. And so now we can go back into this formula and just put in those values. So we get cosine of theta times sine of theta plus 1 plus sine of theta times cosine of theta. And that's divided by, so dr d theta again, so that was cosine of theta times another cosine of theta minus 1 plus sine of theta times sine of theta. So let's try to just simplify this a little bit. I mean, you could definitely just plug in theta is equal to pi over 3. That's where we're doing it, right? We could do that at this point, but I think we'll have an easier time plugging it in if we just kind of simplify things a little bit. So in this top one, we get cosine of theta times sine of theta. And then if we distribute, we get plus cosine of theta. And then we get plus sine of theta cosine of theta. So we can already group together, right? We have 2 times sine of theta cosine of theta. And then in the denominator, we have cosine squared of theta. And then here when we distribute, we get minus sine of theta. And then we get minus sine squared of theta. So there's actually some pretty nice simplification we can do. So in the numerator, we have 2 times cosine of theta times sine of theta plus cosine of theta. And then in the denominator, we have cosine squared of theta minus sine squared of theta minus sine of theta. And so what am I referring to when I say nice simplification? Well, we actually have a couple of double angle formulas in here, and it's not necessarily like a ton easier to calculate this with the double angle formula, but I think it will be a little easier. So here we have 2 times cosine times sine. That's the same thing as sine of 2 theta. Maybe let me color code this. So sine of 2 theta is the same as what we have there. And then here we have cosine squared of theta minus sine squared of theta. That's the same thing as cosine of 2 theta. So it's just going to be like a little bit less to plug in if we have that, rather than having to calculate cosine and sine and multiply them together. Okay, so now we're ready to plug in theta is equal to pi over 3. So we're going to get sine of 2 pi over 3 plus cosine of pi over 3 divided by cosine of 2 pi over 3 minus sine of pi over 3. Okay, so what is sine of 2 pi over 3? Well, if you go on the unit circle, maybe I'll just quickly sketch this since they're all going to be either with 2 pi over 3 or pi over 3. So pi over 3 has coordinates of 1/2 and square root of 3 over 2. 2 pi over 3 has coordinates of -1/2 and square root of 3 over 2. And so sine of 2 pi over 3 is going to be equal to square root of 3 over 2. Cosine of pi over 3 is equal to 1/2. And then cosine of 2 pi over 3 is -1/2. And then we are subtracting sine of pi over 3, so we're subtracting square root of 3 over 2. And so notice that the numerator and denominator are the same, they just have a negative sign introduced, and so that gives us -1. So if we look back at our picture, that seems pretty reasonable. It looks reasonable that this might be a slope of -1, and then that's what we got. Okay, so now I want to move on to using integration with polar curves. So I'm just going to use this as kind of a sample. Like I'm going to write down a general formula, and this is the same graph that we were working with in the last example, but that doesn't really matter here. I'm just kind of treating this as some generic graph. So let's say that this function here is just theta is a function, or sorry, r is a function of theta. So this is just some generic polar curve. So let's say we wanted to find a certain area of this, and how are we going to measure the area? Well, if you think about it, when we're dealing with like regular integration with Cartesian coordinates, we're going from an x value to another x value, or a y value to another y value, right? You can imagine that you're kind of sliding along the x-axis or the y-axis in order to kind of like delineate the area you're talking about. With polar coordinates, that's not really how it works, right? So the input variable is theta, and so we're not going to be kind of sliding horizontally or vertically to delineate an area. We're going to be kind of spinning around, right? So for example, you could have one initial angle here, and actually let me maybe use a different color. So let's say that this is some angle here, and let's say that this is the angle theta is equal to A. And then we have some other angle, and let's call this angle theta is equal to B. So let's say that we wanted to find this area here. So we can do that using integration. So maybe let me just summarize what we're going to be doing here. We're going to be finding areas bounded by polar curves. Okay, so just like with the last one, I'm going to start by giving you the formula, and then we'll look at the proof. And I think the proof is pretty nice for this. It's very similar to this idea of adding up rectangles, but in this case, instead of adding up rectangles, we'll be adding up these like wedges. But anyway, let's write down the formula. So the area of the region bounded by a polar curve r is equal to f of theta from theta is equal to A to theta is equal to B is given by the following integral. So it's going to be the integral from A to B of 1/2 times r squared d theta. So we're integrating with respect to theta. And by the way, remember that r is a function of theta. So you're not actually going to have the letter r appearing in your integral. You're going to be replacing it with whatever your function is. Okay, so I want to show you the proof of this. And so there's one thing that we need to do before kind of jumping into the proof. So as I mentioned a moment ago, if we think about how we would go about proving this, we're going to divide this area up into pieces, right? That's how we usually go about proving these integration formulas. But the pieces we're going to divide this up into, they're not going to look like rectangles. They're going to look kind of like pieces of a pie. So basically there's a new kind of shape that we need to know how to find the area of, because we're not just going to be adding up rectangles, we're going to be adding up these sort of pie pieces. So the first thing we need to do is learn how to find the area of something called a sector. So the area, so what do I mean when I say a sector? So a sector is basically kind of the fancy name for if you have a circle and you cut out a piece of it. So let's say we cut out a piece that looks like this. So let's say we're trying to find the area of this piece here. Well, there's an angle associated with this piece, right? We can call this angle here, let's call that theta. So how would you go about finding this area? Well, you can think about kind of proportionality, right? So let's say that you were trying to find the area of the whole circle. So the area of the whole circle would be pi r squared, right? And so if we want to kind of compare the area of this blue region to the area of the whole circle, we could write it as a ratio. So I'm going to use lowercase a to represent the area of this sector. So we have a over pi r squared, right? That's like a fraction that represents the proportion that this piece of the circle is as a portion of the whole circle. So what should that be equal to? Well, whatever that ratio is, that should be the same ratio that we get if we compare the angle theta to 2 pi. So where is that 2 pi coming from? 2 pi would be if you were to go all the way around the circle, right? That's like the full number of radians contained in the circle. So just to kind of give an example, like let's say that you had a quarter of a circle, just to kind of really convince you why this works. Let's say you had a quarter of a circle. Right? If you had a quarter of a circle, well, what angle would you have? You would have an angle of pi over 2. And pi over 2 is 1/4 of 2 pi. And so this area is also going to be 1/4 of the total area. So that's all that we're really saying here, is that if you compare the angle to the total number of radians in the circle, that's going to be the same as comparing the area to the total area in the circle. And so if you simplify this equation, so let's say you cross multiply, so you get 2 pi times a is equal to theta times pi r squared. And we're trying to solve this for a. So we can cancel out a pi from both sides, and we can divide both sides by 2, and we get a is equal to 1/2 times r squared theta. So that's how you find, in general, this isn't calculus, this is just how you find the area of a sector. Okay, so now let's see how we can use this. So I'm just gonna copy and paste this so that we can refer to it. Okay, so as I kind of started to mention, if you wanted to approximate this purple area, you could do so by breaking it into these slices. So I'm just going to draw like 3 slices here, but really you would probably be doing more. And I'm going to kind of highlight one of them. So let's say we're looking at this slice here. Okay, so let me kind of write that down. So to approximate the area, I'll just say the purple area, what we can do is we can break it up into these slices, right? They kind of look like slices of pie. So these slices are not actually sectors of a circle, right? If you kind of look at the edges of them, they don't look just like this, right? They don't have like a perfectly round edge to them because this isn't a circle, right? It's a different shape. But just like how, with a function, it doesn't actually break up into rectangles, this doesn't actually break up into sectors, but they're pretty close. So we can approximate these as sectors. So these slices are kind of like sectors of circles. So how would you approximate the area of one of these slices? Well, you could say that, so let's say that we have 3 of them here, and so we would call them like A1, A2, A3. So let's say that this one, for example, we can call AI, right? So we're trying to find the area of this sector or of this slice. So the area of one slice would be AI is approximately equal to 1/2 times r squared times theta, right? That was our formula that we just talked about above for the sector of a circle. So what is the r in this picture? Well, the r is just the radius, right? So we're basically kind of pretending that this orange slice is a piece of a circle. And so what would the radius of that circle be? Well, it would be defined by this function, right? This is the function that tells you for a particular angle theta, how far out you go. And so the r that we're talking about here is really just kind of the radius of, or the distance of this orange slice. And so I'm actually going to call it Ri. So Ri refers to basically like the length of that piece. And then what's the angle? Well, instead of calling it theta, here we have these small slices, and realistically we would actually be breaking this into even smaller slices. Just like with a function with rectangles, we would break it into like teeny tiny rectangles. And so let's call this angle here, let's call it delta theta, right? So delta theta means like a small change in the angle, and so we can call this angle delta theta. Okay, so how would we find the total area? Well, the total area would be approximately equal to what we would get by adding up all of these little slices, right? And so that would look like the sum from 1 to n of all these areas. And so that would be the sum from 1 to n of 1/2 times Ri squared delta theta. And then how do you find the actual area? Well, at this point, hopefully this idea is familiar. The actual area, actually, I don't want to confuse that with total. I'll just write it here. So the actual area would be taking the limit, right? The limit as n approaches infinity of this sum. And so what would that come out to be? Well, that would turn into an integral. So it's going to be an integral of 1/2 times the radius squared, and then delta theta turns into d theta. And that's exactly the formula that we had written above. Right? If we go back up here, that's exactly the formula I told you was the case. And so really this formula just comes from this fact here. This is just really the kind of important fact that leads us to that integration formula. Okay, so let's take a look at a couple of examples using this. So the first example I want to do is I want to find the area enclosed by one petal, or sometimes they'll call it a leaf, of the graph of r is equal to cosine of 2 theta. So we looked at this graph in the previous video. So we could choose any of them that we want. It doesn't super matter, but let's choose this one here. So let's focus on finding the area of this petal here. So we need to figure out what the bounds are going to be, right? That's really the only thing that we have to figure out here, because we have our formula. We know that r is equal to cosine of 2 theta. We just need to figure out the bounds. So basically, look at where this purple petal falls. It falls in between negative pi over 4 and, oops, that's not right, positive pi over 4. And if you go back to the video from last time and we actually went through and graphed this, we started, I'm pretty sure we started our table at negative pi over 4, right? And we saw that as we went from negative pi over 4 to positive pi over 4, that's what gave us this whole shape. So you would want to just be careful when you're choosing your bounds that you're really choosing kind of the starting point and ending point of the part of the graph that you're looking at. Okay, so what do we want to do here? We want to do the integral from negative pi over 4 to positive pi over 4. And our formula is 1/2 r squared d theta. So what is r in this case? And let's actually pull the 1/2 out of our integral. So what is r in this case? It's just cosine of 2 theta. So we're just taking cosine of 2 theta and squaring it. Okay, so we're going to use an identity to be able to evaluate this integral. But before we do that, there's an observation that will make this a little easier, which is that this is symmetric, right? We can see that if you were to go from, instead of going from negative pi over 4 to positive pi over 4, what if we started at 0 and just went from 0 to pi over 4? Well, that would give us half of the area, right? So what we can do is we can rewrite this as 2 times 1/2 times the integral from 0 to pi over 4 of cosine squared of 2 theta. It would work out totally fine if you left the bounds as is, but this just makes it a little bit easier. Okay, so next thing I want to do is, or next thing we need to do is basically rewrite this using an identity. And so there's an identity that says that cosine squared, and I'll write it kind of like this, I'll say cosine squared of A is equal to, in general, 1/2 times 1 plus cosine of 2A. And so in this case, what is A? Well, A is 2 theta. And so what are we going to have here? We'll have, 2 theta here, and here we'll have 2 times 2 theta, which is 4 theta. So we're going to end up here with the integral from 0 to pi over 4 of 1/2. And actually, let's pull that 1/2 outside of the integral. And then we have 1 plus cosine of 4 theta d theta. So now we can just break this up and integrate each piece. And so we're going to get 1/2 times, so what's the antiderivative of 1? That would just be theta. And what is the antiderivative of cosine of 4 theta? Well, it's going to be sine of 4 theta over 4. So that's, you could do a u substitution, but it's kind of one of the simpler substitutions that you might be able to just do in your head. And we're evaluating that at pi over 4 and at 0. So if we plug these in, we get 1/2 times pi over 4 plus sine of, so we have 4 times pi over 4, so that's sine of pi. And then from that, we're going to subtract 0 plus sine of 0 over 4. So that's all, that second part is just equal to 0. And so we're left with 1/2 times pi over 4. So sine of pi is also equal to 0. And so this simplifies to being pi over 8. Okay, let's do one more example. So in this example, we're going to find the area, the area of the region that's basically inside of r is equal to 3 times sine of theta, and outside of r is equal to 1 plus sine of theta. So what does that area look like? Well, so 3 times sine of theta is this circle, right? And so inside sine of theta would be all of this, or 3 times sine of theta, sorry, would be all of this. But then we want to be outside of the cardioid. So the cardioid is the 1 plus sine of theta. And so that leaves us with this area here. This is the area we want to find. Okay, so we're going to have to do some subtraction in order to figure out what this area is, but the first thing we want to figure out are what are our bounds. In this case, because we have the picture, we know what they are because, I graphed it on Desmos, so we know that these are the correct bounds. So the bounds are going to be pi over 6 and 5 pi over 6. How could you figure that out without having it graphed? So you could just set the two functions equal to each other, right, and solve for theta. So to find the intersection points, you could set 3 times sine of theta is equal to 1 plus sine of theta. And then from here we can subtract sine of theta from both sides, so we get 2 times sine of theta is equal to 1. And so that means that sine of theta is 1/2. And so what are the angles that give you sine of theta is equal to 1/2 when you're between 0 and 2 pi? Well, one would be pi over 6, and the other one would be 5 pi over 6. So theta is equal to pi over 6 and 5 pi over 6. So those are our 2 points here. And we can see that as well on the graph, that those are the intersection points. Okay, so how are we going to find this area? Well, what if we were to just integrate? So if we were to integrate from pi over 6 to 5 pi over 6, the circle. So that would be 3 times sine of, or sorry, let me put in the whole formula. So 1/2 times 3 times sine of theta squared d theta. So what area would that be giving us? Well, that would give us the area of this entire circle. So how can we kind of get rid of that extra part that we don't want at the bottom? Well, we can subtract out. So if we instead were to integrate the second function, so the cardioid, from pi over 6 to 5 pi over 6, that would give us this green area. And so that is going to, if we subtract that out, that is going to then leave us with the area that we want. So what we're going to do is we're going to subtract out. So we start with the using the outer function as our function, and then we're going to subtract out the integral from pi over 6 to 5 pi over 6 of, now we're going to use our function being the inner function. So that was 1 plus sine of theta squared. Does that make sense? So we have our outer thing and we're subtracting the inner thing. It's kind of like we've done similar stuff like this earlier, right? Where you have your inner function, outer function, or top or bottom function, and you're subtracting them to find the area that's kind of between them. Same idea here. Okay, so there's one observation kind of like what we did last time that will make our lives a little easier. And actually, let me kind of put something in here. So this is going to be, so this was pi over 6. This was 5 pi over 6. Let me do that a little better. But just like what we did with the last one, we can use symmetry to kind of make things a little easier. So instead of going from pi over 6 to 5 pi over 6, let's go from pi over 6 to pi over 2, and then we'll multiply our answer by 2. And the reason that's going to be easier is that think about what kind of results you get when you plug in pi over 6 into sine and cosine versus plugging in pi over 2, right? Plugging in pi over 2, you get 0 or 1. And those are just much nicer numbers to deal with than having to deal with 1/2 and square root of 2, or square root of 3 over 2. So we're going to rewrite this whole thing as basically multiply by 2. And I'm going to combine these also into one integral. So I'm doing kind of 2 steps at once here. So we're going from pi over 6 to pi over 2. And so that's where this 2 came from. And then I'm just going to put both of these together into one integral. And also this 1/2 came from pulling it out from both integrals, right? So we're left here with 9 times sine squared of theta. And then here we'll have minus, because of this negative sign, 1 plus sine of theta squared d theta. So I know I did a few steps at once, but again, what are we doing? We're multiplying by 2 because we're changing the top bound. I also pulled the 1/2 out that came from here and here. And then the last thing I did is I put the two integrals together. So I distributed this into being 9 times sine squared of theta, and then I subtracted our integrand here. Okay, so why did I combine these into one integral? Basically because if we multiply stuff out, some stuff is going to cancel and it will be kind of easier than doing each individually. So this is going to give us the integral from pi over 6 to pi over 2 of, so we have 9 times sine squared of theta minus, so if we multiply this out, we're going to get 1 plus 2 times sine of theta plus sine squared of theta, d theta. And so if we combine this, we're going to get the integral from pi over 6 to pi over 2 of, so we have 9 times sine squared of theta, and we're subtracting from that sine squared of theta, right? So it's going to leave us with 8 times sine squared of theta. And then we're going to have minus 2 sine of theta minus 1. Okay, so from here, it's basically pretty similar to the last one that we did, right? So the first thing we need to do is rewrite this 8 sine squared of theta. We can rewrite it using one of the identities. So we know that sine squared of theta can be written as 1/2 times 1 minus cosine of 2 theta. And so let's put that into our integral. Pi over 2. So when we multiply the 8 by 1/2, we'll get 4, right? So we have now 4 times 1 minus cosine of 2 theta minus sine of, or minus 2 times sine of theta minus 1. And so now we can distribute this and we end up with so we have 4 minus 4 times cosine of 2 theta minus 2 times sine of theta minus 1. And so now we can just go ahead and integrate each of these pieces. So for the first part, we're going to get 4 times theta. For the second part, we're going to get, so the antiderivative here would be sine of 2 theta over 2, and then we're multiplying that by 4. So we have 4 times sine of 2 theta over 2, right? But we can simplify this, right, and just rewrite it as 2 times sine of 2 theta. And then we have, what's the antiderivative of sine of theta? Well, it's negative cosine of theta. So this becomes plus 2 times cosine of theta. And then we have minus a theta. So actually, let's just combine that and make this into 3 theta. And we're doing this at pi over 2 and pi over 6. Okay, so we end up with 3 times pi over 2, so 3 pi over 2. Minus 2 times sine of pi plus 2 times cosine of pi over 2. And then from that, we're going to be subtracting 3 times pi over 6. So 3 times pi over 6 is pi over 2. And then we have minus 2 times sine of pi over 3 plus 2 times cosine of pi over 6. All right, so that's 3 pi over 2. Sine of pi is 0, so we can get rid of that. Cosine of pi over 2 is also 0, so that all goes away. Then we have minus pi over 2. And then here we have, so sine of pi over 3 is equal to square root of 3 over 2. So maybe let me write this as an intermediate step so that you can follow. So this is going to become plus, right, 2 times sine of pi over 3. And then this is going to become minus 2 times cosine of pi over 6. And so here we have, so 3 pi over 2 minus pi over 2 is just going to be pi, right? It's 2 pi over 2, which is just pi. So we have pi plus, so here sine of pi over 3 is square root of 3 over 2, so this just becomes square root of 3. And then cosine of pi over 6 is, so pi over 6 cosine is square root of 3 over 2. So again, we have root 3. And so the root 3's cancel out, and we're left with pi. So kind of a doozy on this one, but really, most of this is just being able to integrate trig functions and, remember the details of how trig functions work. And other than that, it's just kind of this new formula for the area. So just like I said on the last couple of videos, I will be giving you all of these formulas on the final exam. So I don't expect you to memorize these. I just expect you to know how to apply them. So that's it. That's the last video for this quarter other than the review videos. So yeah, thanks for watching all these videos, and I will see you in the review videos.